and one-time programs.
Okay, thank you very much. Can you hear me? Because I think I'm wired to a lot of speakers, but as far as I know, none of them exactly work. So my topic is program obfuscation and one-time programs. And okay, so cryptography in the basic form, which you probably studied in your cryptography courses, talks about controlling access to data. And we have fantastic solutions for this. We know how to encrypt data. We know how to make sure that data satisfies integrity, it's authentic. And the thing about controlling access to data is that once you give access, so once you see, let's say, unencrypted data, then the whole story is gone, right? There's nothing more to control. There's nothing more to hide. So today, I'm actually not going to talk about controlling access to data, but actually on the question of whether we can control access to programs. And when you talk about controlling access to programs, there might be a variety of goals that you have in mind. I'll talk about two goals today. So the first goal is that you might want to give someone the ability to run the code, but not necessarily the ability to learn the underlying algorithm. So they can run the code for as long as they like. It's their code, but they shouldn't be able to learn what idea went into this code. And the second goal, which people have considered less, is perhaps I want to give you my code. I want you to be able to run it for a limited amount of time. Maybe I want you to be able to run it once. So you want to be able to run it in a later time. You maybe want to choose whatever inputs you run it on or input that you run it on. But I don't want you then to be able to go on and run it again and again and again. So obviously, not only that I don't want you to learn the algorithm, I don't want you to even learn the ability to run it one more time. So these might be two goals. You may think of other goals associated with access to programs. And those are two goals that I'll talk about in the talk today. So just sort of to recap where we're at, obviously if I give you code, if I give you executable code, it doesn't look like a black box the way that we write code today, but in fact you can find out a lot about the underlying algorithm. If you look at the straightforward way that executable code works, and this could be code for anything. It could be whatever code is hiding in your Skype program or in the music program or PDF and so forth. So that's a fact of life right now. And what I'll show in this talk from a theoretical point of view, so we want to formulate these problems, these goals, goal 1 and goal 2, and then we want to talk about what can we do about them. You here for the speaker? We've given up on it. Okay. So the question in this talk is, can modern cryptography, can techniques from sort of the more classical cryptography that we've developed help toward this goal of controlling access to programs? And the talk, in some sense, is divided into two parts. The first part, I will show that if we talk about the first goal, where I want to give you code, and you can execute for as long as you like, but you shouldn't learn the underlying algorithm, then we'll show that actually that's the situation is not good. So these are negative results. So in other words, we want to show that if you only use software-based techniques, so you only use algorithms and mathematics and so forth, then you can actually prove that there are certain kind of functionalities or programs which are impossible, where it's impossible for me to give you the ability to execute and yet prevent you from learning the underlying algorithm. And that's called in the jargon, it's impossible to do program obfuscation. I'll talk first half of the talk about really how we define program obfuscation from a theoretical point of view, and then how we show negative results on it. And in the second part of the talk, because in cryptography we've actually had a lot of luck. So at least since I've been in the field, and I think since sort of mid-70s, everything you want to do in some sense you are able to do. You want to hide encryption extremely well. There are these amazing results. You want to digitally sign. You want to have zero-knowledge protocols. You want to have multi-party protocols. Now there's this amazing homomorphic encryption results out. So it's very disappointing that you can't do it. And the suspicion is that we just didn't define it right or something. Okay. So in any case, the second part of the talk is going to have positive news, but with a cost. So what we're going to do is we're going to add to the idea of using just software or mathematics and algorithms, we're going to add some secure hardware. In fact, it's going to be some secure memory, and I think it's a very simple secure memory, and I'll show you what it is. And then we say that if you use algorithmic techniques, plus you have the ability to use this secure memory, then you will be able to address the second goal. Remember, the second goal was that I let you have the program, and I want you to be able to execute once and no more. Okay? And we will show in the second part of the talk how to do this. How to essentially take any program and enable a one-time execution of it. So it won't be just for special programs, but it will be a transformation, taking any program into this kind of one-time mode. Okay, so this is what the talk is about. And let's start with the first part. So the first part talks about, again, the goal, the more traditional goal in controlling access of programs, which is I want to give you code. You can use it as long as you like, but I don't want you to learn anything about the algorithm. Now that's called program obfuscation. That's a short term for that long description. Program obfuscation, if you think about it pictorially, is essentially a way to take a program. So what's a program? We have to define how it's given to us. I won't do it for this talk. You could think of it as just an algorithm, you know, or you can think of it as a circuit. So there's a circuit, sort of pictures of gates hiding. That would be sort of a more difficult situation to address, so we want to address that situation. Or you can think of it as executable code. Just you have some sort of intuition of what it means for a program. And what an obfuscator does, this OBF there, is that he takes this code and he scrambles it around. So it sort of has a mixer there. And at the end comes an obfuscated program, which has the same input-output behavior as the original program. So on the same input, it gives the same output as the original program. However, somehow, it's impossible to reverse engineer this obfuscated program. And now we have to define what we mean. But intuitively, the idea, again, is that it's from obfuscation of P, you can run it, get inputs and outputs. But other than that, it looks totally like, you know, spaghetti. OK. Now, before we get to the definition, which is sort of more mathematical, let's see how useful such a tool would be. First of all, in practice, in the real world, people have been doing obfuscation and using obfuscation for a long time. This is not something that theorists, you know, this is not a zero-knowledge proof. It's not a theoretical concept. It's something that in practice people want to do. So for example, why would you want to do it? So the simplest application is for copy protection or digital rights management. So the idea is here. Suppose I have a program. And I only want privileged people to use it. Privilege may be defined as people who know a password or have certain kind of hardware or whatever. So I take my program and I put in a couple of lines of code with a test that says only if the person who's using this program knows a secret, has a hardware or something, run the program. Now, obviously, if I just give you the program, the first thing you want to do before you give it to your friend who doesn't know the password or doesn't have the hardware is find those lines and remove them. So I want to give you the program in such a way you won't be able to find those lines. So if I obfuscated the program and then gave it to you, you will be able to run it, but you'll never be able to find that test. So that's sort of how obfuscation is used for digital rights management. The problem is, and then there are other, so essentially, you know, these obfuscators are very important in order to prevent competitors from looking at your code and copying it, you know, doing better than you, from preventing hackers from looking at your code, especially hackers in online games, apparently. It's very important that they won't know how to beat the game because then the game's not very much fun. Watermarking and so forth. So the thing is that it's obviously very important in all these settings and used. Okay, now the question is how well does it do? And we'll talk about that in a minute. I want to just point out that it's not only, it turns out that the existence of obfuscators is important for practice, but it turns out that it is would be extremely useful as a tool for cryptographic research. So if you think about these, if in fact it was possible to obfuscate it, it was possible to take a program and scramble it so you know nothing about the underlying algorithm, you could solve, you know, a ton of cryptographic challenges in a very simple way. And we would make our life as researchers much simpler. You could, for example, do things like delegate cryptographic ability. You could have automatic transformation of private key algorithms, symmetric algorithms to public key algorithms. Essentially, you do everything in private key, and then you have obfuscated, and that would be sort of, and give it to someone the public ability to run it. Essentially, I would dare to say that you could write a very simple program and then obfuscate it and solve almost every cryptographic task I can think of. Okay, so essentially what I'm saying is that if we could do it, it would be very nice. Okay, but recall that to begin with I said that you can't do it. Okay. So still, let's go on with it. What if we could do it? Okay. So let's look at this delegation of cryptographic ability application. So here, let's say that's me or someone or me a few when I was born. Anyway, and I have a digital signature scheme. So I have a public key and a secret key. Only I know my secret key. Everybody knows my public key, so they can verify the signatures are mine. I go on giving a talk here, November 09, and I want to let my assistant Bob to sign messages while I'm gone. Okay? So what could I do? One thing I could do is I could give him my secret key. However, my assistants have a tendency of changing, and I don't want to give him my secret key. Okay, so because then when he goes away, he keeps signing my messages. So another thing I could do is I could essentially modify my signature algorithm to have a little command in it, that says only work on the date of May 09. Oh, well, I didn't change that part of the slide. Only work during November 09. What's the date today? The 9th? Yeah. And other than that, don't work. And I give it to my assistant. He wants to remove that. Of course, he removes that warning. So then I obfuscate. And then everything is good. If there was a good obfuscator, my assistant can run that program, but the program will stop working, assuming that there's a clock and the program accesses the clock after this date. So obfuscation, again, is obviously not just good for preventing reverse engineering, but it's also good for things like cryptographic delegation of capabilities. All right, so are there obfuscators? So you can go and buy some. I mean, this is, I think, this slide is from a couple of years ago, but I'm sure today you could get lots of other products. And the typical solutions are to do essentially security by obscurity. So you take code, and you all know how to write, it's sort of a natural instinct how to write code like that. You write variables with bad names, and you have things jumping around, you have nonsense instructions, you encrypt code segments, you do all the kind of things that they tell you not to do in software engineering courses, and then it looks hard to break, but that really only looks hard. The truth is that these things are usually very easy to break. So here's some quote from a Yahoo blog where they say, then there's the question of code privacy. This is a lost cause. There's no transformation that will keep a determined hacker from understanding your program. This turns out to be true for all programs in all languages. The privacy benefit provided by obfuscation is an illusion. Okay, so that's what they say. So now the question that we want to ask in this talk, is this really true? There's no program that you can obfuscate? Can cryptography help a little bit? Can cryptography help a lot? But the situation in practice is that I think one of my students was visiting Microsoft, and she was had part of her interview was with people who do obfuscation. I think it was in Redmond or something, and she asked them, so when you actually come out with one of these products, how much time does it take till people break it? And they said something like, well, if it's 24 hours, we think it was a good program. So these things really are not, they don't work very well in practice. But that might be because they just don't have the right ideas, okay? And that's what we'd like to find out. So the focus will be a theoretical study. We want to, first of all, define obfuscation without just a picture, but some sort of mathematical definition. The first definition was proposed in this paper, a very well-known paper by Barak, Goldwasser, Impagliazzo, Rudish, Sahai, Vadan, and Yang. And they call it a virtual black box definition. I'll go through it. There's other definitions with this best possible obfuscation definition with a student of mine, Guy Rothblum. And then once you have a definition, now you can ask mathematically. Maybe it is possible to achieve this definition. And if it's if it's impossible, maybe it's possible for some programs, impossible for other programs. The situation now can be addressed a little bit in a more rigorous fashion. And that's, in a sense, the kind of things that I've been doing on this topic. Trying to say, when can you do it, when you cannot do it, and what will you do when it's impossible? All right, so what's a definition? Okay, so here is a definition of what's called a virtual black box definition. There could be others, okay? This is a very strong requirement from an obfuscated program. And the requirements are here. We want to say that an obfuscator, again, takes a program to an obfuscated version, and it does this for a class of programs. It makes no sense just to talk about an obfuscator for a single program. It has to be sort of a general transformer of class of programs to another obfuscated versions. We want to preserve functionality, obviously, so the input-output behavior has to be the same. So if it's a game, it's going to be the same game. Okay, the game doesn't change. We want to preserve efficiency. So we don't want to obfuscate the program and now have a much slower program. Say to begin with, the program ran in linear time. Now it's going to run in exponential time. The truth is that even if you were allowed that, it turns out that that doesn't help much. But it should obviously be a requirement from a good obfuscator that it comes out with programs that somebody would still want to run. And the interesting part to define, the interesting part to define is this blue part, what does it mean virtually black box? What is it that you really want from it? How do you capture not learning the underlying algorithm? So intuitively we want to say that you don't leak information that's not obvious from the input-output behavior. So there's some things you can't prevent. Just by looking at input-output behavior, you can already learn something. We want to say that you can't do more than that. Okay? So how do we actually define that? So here is a definition. So a definition will start with a picture. So let's think that on the left-hand side, think about what an adversary, this is the guy in the box here, has. He looks at the obfuscated program, so that's the input on the top, and he studies this program and says, okay, now I think I know some property of the underlying program. So this is pi of p. Let's say it's a bit even. A single bit. I've learned a single bit about the original program, original algorithm, okay? And what we want is that so he has some success. Let's say, in fact, the program is the kind of thing where he knows everything. He has some success that he can learn from the obfuscated code. I want to make sure that this success is no better than the kind of success he would have had only looking at input-output relation of the program. So I want to compare that. I want to say this could be simulated by a simulator. So he's not an adversary. He doesn't see the obfuscated code. All he has is black box access to the program. He can only see input-output. And he's still trying to learn the same property that this adversary guy got about the original program from the obfuscated code. And what I would like it to be the case is the success on the left and the success of the right are the same. So if we put some equations here, essentially I want to say that for every adversary which is efficient, there exists some simulator such that no matter what the property is, for every property about the original program, any bit of information, the probability that the adversary could learn it, so he could learn this property, and the probability that the simulator could learn it are very close to each other. So they're sort of polynomially, exponentially close to each other. If you are into these kind of definitions, fine. If you're not, all you have to remember here really is the bottom line is that we're requiring that an obfuscator really should not leak any information, even a single bit, about the original program. And we get at it through this kind of simulation definition, saying that whatever you could get, you could have simulated on your own just from looking at input-output behavior. Okay. Notice there's no clock in this room, which is very good for maybe somebody. Oh, no, there is. Okay. All right. So now that we have a definition, we can start talking about whether it's possible to achieve the definition or not achieve the definition. And the first result, which is the result by Barak and Goldwasser and all those other guys, which I cannot repeat their names again. It's a miracle that I actually got it the first time. Is that they show that actually there exists some functionality, some program, okay, that no matter what you do, so it's a very strong negative result. It says no matter what algorithmic technique you use, you will not be able to achieve this definition. You cannot obfuscate. And they do this if one-way function exists. You can think of that, this is under some kind of an assumption, like factoring integers is hard, or computing some seemingly intractable problems on computational lattices is hard. There's a variety of these one-way function candidates. They say if that's true, in some sense, if encryption exists, okay, then it is possible to show that something cannot be obfuscated. So it's almost going in the opposite direction. It says if you can't protect privacy, then it's impossible to obfuscate a particular program, okay? And the idea of what they show is this weird idea, very nice. It's kind of if people that are from the generation that used to do diagonalization, it is very reminiscent of that, is that they show that the program, they show this particular weird program that cannot be obfuscated. And it's a program that it expects its own code as input, and if it gets it, it outputs a secret. So if you are given obfuscated code, you can feed it into yourself, and then the secret comes out. But if you're only given input-output access, then there's no code to feed into yourself to get the secret. All this has to be exactly formalized, because how can a program actually get itself as input? I mean, after all, the input has to be smaller than the program. But all this can be ironed out. That's the idea. So you think to yourself, she gave this whole speech, we've been talking for 20 minutes, okay, and she shows that this very strange program is impossible. But I don't want to obfuscate programs like this. I never feed myself into my program, okay? So, so the question really is, what does this mean? It means that universal obfuscation can't be done. You can think of weird programs that cannot be obfuscated, but it is possible, say, that that maybe lots of programs can be obfuscated. So in other words, this does not mean that nothing can be obfuscated. Okay? So that's sort of the beginning point of this research. And in fact, there are some programs that can be obfuscated, satisfying that definition, you know, that very strong definition where you can't learn a single bit. So here is one. You know, the sad thing is that it's the only one. But so here's the one, though. Here's the program. The I is now what P was before. So it's this weird program. Suppose that somebody publishes a puzzle in the newspaper, a very complicated puzzle, and you're supposed to. I'm not thinking about a crossword puzzle, and you're working on it. And at the end, you think you've solved it, but you'd like to verify whether you've solved it. So they also publish a little program that if you plug in. So they can't really publish a solution because then everybody's going to see it. So instead, they publish a little program that if you've solved it and you feed in the right solution, the program says yes. Okay? Let's think of that program. You can think of it also as a password program. It's a weird program that all it does is that when it gets X, which is the right solution, it says yes, or otherwise it says no. This program, which essentially just compares whether the input is a particular string, can be obfuscated. You can put that, you can transform it so that now, even if I look at it, I can't figure out what this. You know, what the program is doing, and only I can run it. That is, only when I have the right solution and I feed it in, that I will sort of make the program say yes. And now the solution is sort of uses number theory, blah, blah. Let's just skip it. Okay, still, that's one program. Maybe all programs that are natural, okay, maybe programs that do like delegation of cryptographic ability can be obfuscated. You know, that's a particular type of program. A program that does, you know, digital signatures and then obfuscate. Maybe digital signatures can be obfuscated. That would be extremely useful. But what I'll show you now, and this is a result with Yael Kalai, show you, I won't prove it, I'll just say what it means, is that we show that, I'll show you an attack on obfuscated programs, okay? In fact, we call it a multiple obfuscation attack. So that under this attack, you can actually prove that not only that weird program of Barak et al. Cannot be obfuscated, but lots and lots of programs, including digital signatures of the kind that you need for delegation, cannot be obfuscated. It's just not going to be that simple to obfuscate my program and send it over to my assistant. Okay? So what is this multiple obfuscation attack? So the one worry about this talk is that he can become obfuscated. So you should ask me questions, okay? You really should feel free to ask me questions. So here's this idea of this multiple obfuscation attack. So let's go back to the application, and this way we'll see what the idea there is. So again, I want to go, and I want to go away. I have obfuscated my signature scheme that only works in October 08, and I sent it to my assistant. But suppose now I want to go again. And now I want to go in November 08. And what I do is I take the original signature program, I say, okay, now sign only in November, and I obfuscate it again. So what I'm saying in this example is that it's very unlikely you only obfuscate your program once, or one version of your program. So in the case of digital signatures, I might want to go several times. I want to delegate my ability maybe to different people, or even the same person multiple times, that under different conditions they can run that cryptographic ability. And now this Bob guy, he's got more than he had before. He has essentially the obfuscation applied to two variants of the same program. And what we could show are examples where in fact, you could even you can recover the secret key from getting these two variants. Okay? So then you could say, well, maybe you should never really let Bob see your signature. You should never obfuscate your program twice. We could show something even worse, that even if you know, someone who's completely unrelated to me, you know, they're blonde, and they have their own digital signature program that uses a completely independent secret key which they've chosen, but Bob is their assistant, they've obfuscated their program. It's not really a question of assistant, it's just that you see a bunch of obfuscated programs in the internet. Then it is possible to recover some information which is a function of both underlying programs okay? Where it wouldn't have been, maybe one obfuscation wouldn't be, you wouldn't know exactly what to do with it, but with several of them, you can actually build up information. So it's a bit pathological, but it's doable. So in any case, what is this saying? First of all, it's saying, this example is saying that this definition with the virtual black box is not really strong enough. Because you should really require that the adversary, let's see, is not only the obfuscation of the program, yeah?
Does Bob have access to the obfuscation function, or just the output?
So the obfuscation function is probabilistic. So it's sort of a public algorithm, but it uses coins, which he does not have access to. And it might have a secret key also. So you think about it just as coins. There is information. The obfuscation takes as input the program, and also it's a probabilistic transformation. Okay? And Bob does not have access to that. Good question. So in any case, what I'm saying is that actually we should strengthen our definition, really, to require that this property that we had before holds even when there's more information around, auxiliary information around, like maybe another obfuscated program, maybe other information is useful in the internet to destroy, the strength of obfuscation. And so you strengthen the definition to hold even when there's this auxiliary information Z. But that's not really my main point. My main point is that once you strengthen their definition to require it to be not to be able to learn any information even when auxiliary information is around, like another obfuscated version of the program, or maybe something else, now you can show a lot more impossibility results. And you can show, in fact, that lots of programs are, like signing, like delegating, are impossible to obfuscate. Okay, so whereas before there was this one impossibility result for that weird program, when you make the definition a little stronger to require security even when there's auxiliary information around, you can show now that lots of programs cannot be obfuscated. So all this was kind of a sad story in the sense that the conclusion is that we can't do it. At least for the definition I proposed. Maybe you could relax the definition. We've tried that. We still didn't manage to get a definition that one can satisfy. So what can we do? So what we're going to do now in the second part of the talk is I'm going to add to the mix some secure hardware. So that's sort of going outside the rules, but I'm announcing it at least. And I'm going to add some secure hardware. And the challenge, of course, is going to be what kind of hardware. Because, for example, I could add a vault with a computer inside of it that does my, implements my program, then give it to you and say, this is the obfuscated program now. Now, you can't get through the vault. You can just ask inputs and outputs. So that's not a good solution. So we want to add very simple hardware, okay, so this whole thing makes sense, okay, and still be able to address our original access control goals, okay? So this just captures what I just said, is that not hardware is born alike, so our secure hardware is not going to be, a supercomputer or a laptop or even a smart card. It's actually going to be sort of a memory stick, but it's going to has some security properties. So it's going to be sort of something that remembers, a device that remembers, but you have some restrictions on how you can access it. Okay, and I'll explain that later on. But you might have that picture in your mind. So what that means, though, is that from here on, okay, my program, when I take a program and then I do a transformation to make it into one of these controlled access programs, the program now consists of software and hardware. And my interface of this program is that I can, I send inputs, I get back outputs, okay? Inside the software, and I could look at this software in the clear completely, but this has to obey the security properties, and the software can talk to this. So it can, I can talk to it as well, but I can only talk to it in this restricted fashion that I have to define. Okay, so from now on, our programs actually are not programs in the sense of only software, but they also have that blue stick, which is secure. The kind that you have is not secure. Because it's sort of misleading that I'm using this picture, but it's a nice picture. So, I mean the blue picture. Okay, so what are we going to get from this? What we'll get is our second goal, these one-time programs. It's what we call them, one-time programs. These are a way to take a one-time program is a program that can be executed exactly once. Okay, so you cannot keep on running it. You can execute it once on an input you choose in a later time. And then it sort of stops living. So here are the requirements. I say that on one hand there's a function like digital signatures. And we say that P is a one-time program for this function. So it's a one-time digital signature, say, if First of all, of course, the functionality is the same. So it will compute exactly the original program, okay, on one input. And two, it satisfies one-time secrecy. So this program will leak no more than the output of the function on a single input to an adversary. So you have to formally define it, but I won't go through that. It's defined very similarly to virtual black box. So you should, in some sense, you are comparable to a simulator who can only ask one question, one input, and get back one output. And and that's even if the adversary has full access to the program. So he can look at your code, the software, he can sort of experiment with the stick, subject to the constraints. Yet this is going to be what we want. And in fact, we'll show that the following theorem, and that is that you can get it. You can compile any function f into one of these one-time programs for f, where the program, again, consists of software and these hardware components. And what I'll do for the rest of the talk now is this. I will, so now we're concentrating on this one-time programs, okay? This is joint work with Guy Rothblum and Yael Tauman-Kalai. And I'll show you essentially, first of all, what's the application of a one-time program? Then what is this hardware? You know, what is the secret hardware? This rock, which I call it. And finally, what is the cost of this compiler? I mean, is this reasonable even? You know, maybe it's a beautiful theoretical result, which actually is fine by me. But still an interesting question. Can you actually apply this and get something that's reasonable in the sense of you want to use it, you want to deploy it? Is deploy the right word? Okay. It's employ, deploy. Whenever I use it, I'm a little doubtful, but nobody's ever put me in my spot, so it's probably the right word. Okay. So what's the difference between employ and deploy then? Employ, right, okay. So let's first talk about applications. So application of one-time program. It's not like obfuscation. It's just a one-time thing. So here, if we go back to the delegation, again, I wanna go, and I wanna let Bob. I say, you know what? I'm going for a couple days. I let him sign 100 messages for me. 100 is a lot, but in any case, I say I want him to sign 100 messages for me. So now I'm not saying that I just want him to be able to sign during the period of November 08 or 09. I actually specify how many times I want him to be able to use my signature algorithm. And then what do? I take my signature algorithm, I convert it into one of these one-time programs for signatures. Of course, one time can be 100 times. You know, it's just the same notion could easily be defined for 2, 3, 100. So I turn it into these things. And what I give him my software, I give him the stick. And now Bob, he can sign for 100 times. But that's it. Okay? So if you think about it, you know, they're always giving these trial versions of software where it's supposed to expire after a day. And then at least I know my son's friends do it. They always set the clock on their computer so that it doesn't ever expire. This would address that as well, right? So because this program can only execute, they can play with it 100 times. After that, it doesn't live anymore. Sort of like Mission Impossible. How many of you have seen Mission Impossible? It's KHD. Ah, very nice. Because sometimes you give audiences talking, you say, Mission Impossible, I've had this, and nobody knows.
Are you talking about the original TV show?
The original TV show, yeah. That's less, okay. No, I didn't mean the movie, okay. When it sort of self-destructs, yeah. That's okay. Yes, okay. So here's an application for one-time program. Here's another application, subway tokens. So suppose you want to generate, generate tokens for the subway that allow one-time access, like a token should, in a subway case. And this question was raised by Blum many years ago in 82 or 83, and then there was a sort of a quantum protocol that was proposed as a solution for this by Broussard and Bennett, and I don't remember who the other two are. So the idea is this: this is the subway in Boston, and you don't want the token just to be a piece, sort of a piece of software, right? Because you can copy it, and then you have lots of tokens. So here's an idea of how you could use a one-time program for it. You think of it as if the subway asks you a challenge, and your token answers the challenge. Okay, and since you don't know, and let's think of it as if it is asking you a random challenge, okay, and you have some sort of pseudo-random function which you compute on the challenge. And therefore, even though if you listen to lots of tokens, you shouldn't be able to figure out how to answer another challenge, okay? So if you had a one-time program for computing such a pseudorandom function, that would be naturally useful in this setting. Now he's coming in. So the subway is asking him, can you compute the function? And he says, here, I got a one-time program, and I can compute the function on whatever challenge you give me, because I can compute it once on any challenge. I have no idea what challenge you're going to give me. Now you give me a challenge, I compute it. But I'll never be able to compute it on another challenge. Seems like an overkill, doesn't it? But in any case, it works. What's another application? He's in. OK, another application is something we call one-time proof. So what's a one-time proof? So proof, those of you who have seen sort of the idea of interactive proofs, I'm thinking of a proof where there's a process, there's somebody who proves it, there's somebody who's checking the proof is correct. And usually if I'm proving something, I can prove it again and again. And then we have these zero-knowledge proofs, right, where you can verify the proof is correct, but you can't turn around and prove it. But I can actually go and I can prove it as many times as you like, because I'm the prover. So the one-time proof has sort of three components. There is the one who actually knows the witness. So he knows the original proof of whatever is being proved. Say that number is a composite number, that he knows the divisor of the number. Or he knows a three-coloring of a graph. So he's the witness owner. And then he wants to give someone the ability to prove this to a verifier. Okay? But the ability to prove it only once. So I want to give you the ability to prove a statement, okay? But I only want you to be able to do it a limited number of times. And again, this idea of a one-time program easily allows you to do so. So I can convince the verifier of the correctness, but I can't do it twice. So for example, an application might be if you're thinking about a voting booth and where people get tokens that allow them to vote, and you want to make sure they don't vote more than once, as they do in certain cultures. So you want them, in some sense, being able to vote is, I prove that I am who I am, that I have the right to vote. I should really be able to prove it only once. It's kind of similar like to the subway tokens. It's just a different type of solution. But the concept, in a sense, is the same. It's an ability that I can perform once and no longer. OK. OK, now, I think that you should be convinced that there are lots of applications to a one-time program. But the really million-dollar question here is, what is the secure hardware that I added into the mix? I claim that it's simple. What is it? So just a word on secure hardware. It's not the first time that people have used secure hardware. First of all, in practice, as you know, lots of these secure processors are around. What do they typically do in practice is that they perform cryptographic operations. So like they can do a decryption operation or a digital signature, and you're sort of assuming that you can't look inside the box that does the decryption or the digital signature. In theory, people have used it too. So in theory papers, people say, well, I'm going to give a solution assuming that there is some functionality which can be done in black box manner, and the enemy cannot look into it. Okay? So there's been lots of usage in theory and practice for software protection, for universal, and for other things, for eCache and so forth. The problem with all of these uses of secure hardware is that hardware really is not a black box. So to assume that there is this box where digital signatures are done, or that's a practical assumption, I mean in practice or in theory, it's actually doesn't stand the test of reality, because there is something called side channel attacks, where people, when you actually are running your computer, that's digital signing or decrypting, someone can be observing you. So they can observe how much power you're using, how much time your machine is taking, how much electromagnetism it's emitting, or, and every day they come up with some other bizarre attack, okay? And it turns out that every computation that you do in hardware, okay, so when you're actually executing a hardware device, to assume that it's black box and nothing has been, and no one can really measure what's going on around it, like how, it doesn't seem to be realistic. Okay, so every computation made in this hardware, in this black box on secret data, will leak something. We just don't know what. Tomorrow, the next wizard will show us, here, this leaks. So I can add to my mix secure hardware, and then they'll break it, and my whole paper is out the window. So really, the logic in choosing which hardware we want is that we want to minimize computation, since computation leaks. Okay, we want to minimize whatever amount of computation is done in hardware. So it's hardware that will do a little bit of computation. In fact, what we want to do, and what we will do, is we're going to eliminate. This hardware is not going to compute at all. Because we're worried that if it computes, then all of a sudden you can measure how much time it took and how much power it took and so forth. So in some sense, what is going to be the point of the hardware anyway? So it doesn't compute, What do I need it for? So let's see how hardware could be useful without computing. Again, the rationale why I wanted hardware not to compute is because I don't want it to be susceptible to these side channel attacks. Okay. So here's my hardware, finally. So I called it a rock, and the idea is this. I want to think of my memory on the stick, okay, as if every memory location is built of two parts. So there's sort of the top and the bottom, or the left and the right, if you like. So every time a memory location has a string in it, it will have actually two. And the way that I can read this memory is restricted in the following way. Oh, it's already reading by itself. So I specify whether I want the top or the bottom. So whether I want the bit to be 0 or 1, and say I specified it to be 1, then the K0 disappear, and I can read only K1. So in other words, what I can do is in a memory location, I can choose whether I want to read the left or the right. I cannot read both. That's the security device. My axis is such that as soon as I ask to read the left, I can see the left. I can see it again and again, but the right gets erased. You can either think of it as being erased, or you can think of it as there's some tamper-resistant bit that says you should never be able to, that's set to 1, says that's it. You can't ever see the top part of the memory location. So it's a rock for read one key, only one of the two, and erase the second. Now I claim this is simple. I mean, it's easy to explain. I already explained it. So that means it's easy to scrutinize. You don't like it, that's fine. It's your prerogative. But it's at least I didn't hide anything under the rug. Okay. Now the question is, of course, whether you can build it. And that's something that one can discuss. Maybe we can discuss at the end. But what we will show is that it's universal. That if I have these kind of components, this kind of memory, I don't need different memory for different programs. It's the same kind of unit which will enable me to transform any program to a one-time program. And for people who know what oblivious transfer is, it's really inspired by it. In oblivious transfer protocol, you can learn 1 out of 2 secrets. The thing here is that there's nothing, the oblivious doesn't really matter to me. I don't care which, whether, I'm not trying to hide whether I've learned K0 or K1, but I want to make sure I only learned one of them. The important thing is, vis-a-vis my previous discussion, is that this piece of secure memory doesn't do any computation. There's no computation that's done here. Because the key that you actually asked to see, you could see it. But the key that you don't see, that you didn't ask for, okay, the one which is erased, is never used in the computation at all. So you've never actually computed on it, and therefore will never leak something from it. So this hardware, in a sense, is weird. It prepares 2 pieces. You choose whether you want to see the left or the right, and the other one just disappears forever. And I claimed that if we're worried about side channel attacks that result from computation, okay, then you don't have to worry about it, because there is no computation on the part that you don't use, on the part that you didn't ask to see. It's just never used later, earlier. You could say, in some, Adi Shamir pointed this out to me, is that erasing something is a computation. And he's right, because if you erase one string versus another string, something different may come out. And that's what he suggested to me, that instead of erasing, what you should do is you should set a bit that is a tamper-resistant bit that goes from 0 to 1 to say, don't ever answer show this part of the key, so the top part, in case that's the one that was supposed to be erased. Okay, that's the hardware. Now, what is the cost of this compiler? That's the third thing that I promised to talk about. So I claim that you could take any program and transform it into one of these programs. I'll even give you an idea of how, because I see we have time. I must have spoken really quickly. But first, let's talk about cost. So my first take here, the cost will be terrible. So the cost is this. So remember, the theorem was that if there's these one-way functions, then I can compile any function f into a one-time program for f. And I claim now that actually it's going to be secure against these computational leakages because of the kind of hardware that I chose. The program will have software, and we'll use n of these rocks. So it's not n blue sticks. It's the same blue stick, but it's n memory locations. Okay, so if the input is size n, there's n of these memory locations. That's not too bad. So it's independent of the size of the program. It could be a very large program, but the number of these secure memory locations you need is the size of the input. But what about the other costs? So there's latency. That's not going to hurt me. Latency, I mean how much time it takes me to talk to the hardware. So I only have to talk to the hardware once, actually. And the total runtime of this new one-time program will be whatever the old runtime was, T of n, times some security parameter, so it's a little slower, but by some fixed parameter. And the hardware runtime is not bad either. So n is the length of the input, and again, times the security parameter. What's bad is the size of the program. So remember, the program had software and that hardware stick. So the software part, okay, which is in the clear, is going to become, in this particular version of the theorem, very large. So I took a small program, you know, like the kind of small C program or whatever. C is probably out, Java, whatever. And I made it into a really large piece of code. How large? As large as the running time, actually, of the original program. So I took a program which had been fixed, you know, 10 lines, but ran for a long time, and I outputted a program whose length is the running time of the original program. That's terrible. We will actually improve this as the talk progresses. So we can, using these new results on homomorphic encryption, get this down to something that's independent of the running time of the program. So it's not going to be the running time of the original program, but again, it's going to be something, sort of a function of some security parameter. So actually, at this point, you can do these transformations, and it's all, yes?
N ROKs, there is
N pair of these keys. Yes, exactly.
The other question was about, can we take this mechanism and apply it to access control policies? For example, access control policy is a program itself, which dictates how many times a given program will run. So if we get n, if we, in a way we get, I think that this is like an secure operating system executing this one-time program once. So and n is an input to that operating system, saying that run it n times. So can I make n as variable, and then so that n can be dictated by an access control policy program?
Yes, but the thing is that if for every n, there will be a different size software. So in some sense, you tell the size of the one-time program depends on n. The way that so for you, you're thinking about n as an input, and that's fine. You tell me that's going to be the n. Now I'm going to make a larger program, okay? However, for the second version, we have to see. We'll come up what happens to your question. How does it work? Let me give you just a hint, okay? Okay, so so those of you who are familiar with this might be some useful, but I'll actually give you an insight into what these words mean. So there's something called the garbled circuit method that Andy Yao came up with in '85. And the application there was how two parties can communicate have a protocol with each other so that I have X, you have Y, and we want to compute some function on X and Y so that at the end we both know the functions, but I don't know your Y and you don't know my X. So let's say the example that often people use is the millionaire's problem, which I don't think applies in our case. But I'm a millionaire, you're a millionaire, I have X, you have Y, and not enough that we're millionaires, we also don't want you to know, we want to know who is richer. And, but I don't want you to know how much money I have. So we just want to know whether X is greater than Y. So that's an example, let's say, of a two-party function where we want to hide the information of the inputs. And he had a method that showed how to do these type of protocols, okay, which is called the garbled circuit method. And it turns out that you can adopt it to the purpose of one-time programs, okay, using these rock hardware. So you can adopt it. You can't use it exactly as is, but it's not that hard to adopt it. So here's the idea of Yao, which is a wonderful idea, and kind of complicated. So I'll just give a glimpse of it. Okay. So what he does is this. He says, all right, let's take the program. In fact, I'm not going to talk about this two-party thing. I'm going to talk about it in our setting already. Let's convert it to this one-time program thing. So let's take the program, the function f, which I'm trying to make one time. Okay. Then there's a known thing is that you can take the function and sort of and make it into a take an algorithm and make it into a circuit where if the algorithm ran in polynomial time, then the circuit is of polynomial size. So that's where the size of comes in, why the software gets larger. So you now think of the new software as this circuit, okay, ands and ors, which implements the original program. Now the thing is, I don't want to give you these gates because then you know what the program is, and the whole point was I was trying to hide what the program is. So now he garbles it. How does he garble it? In a second, in the next slide, I'll actually give a hint of how. But let's say that there's some way, okay? What he does is this. He says, he next to each gate, like an AND, an OR, and so forth, he puts on every wire coming into the gate 2 keys. Okay, because every input to the gate it's a Boolean input. It's either 0 or 1. So he puts a key that corresponds to 0 and a key that corresponds to 1 on every wire, and also on every output wire. And now what he'll do is he actually will make the outputs of the gates to be these encrypted, what he called encrypted truth tables. The idea is that you can figure out what is the key that you've computed with respect to the output wire, if and only if you knew the keys on the input wires. Okay, so there is a way that if you know the keys on the input wires, you can figure out the keys on the output wires on the next levels, and so forth, and propagate to the top. Okay, and so he gives you this whole garbled circuit, these encrypted truth tables, and the key to running the whole thing is to start from the bottom. So you need to know the keys that correspond to the input wires. Now, if you knew the key that corresponds to every single input wire, every pair, then you could run this circuit on all possible inputs. But if you only knew one, so here are these pairs. So let's say K10, K11 are the pair of keys that correspond to this input wire all the way on the left. And then for each input wire, there are pairs. Now, when you select actually a particular input to enter into this circuit, that's as if, let's say you wanted to run it on X, where the first bit of X, X1, is 1. So that would mean that you need this key, because the 1, 1 corresponds to a bit 1. And so forth, okay? So what essentially Yao's thing does is it says if you know the right keys that correspond to your input bits, then you have, and somebody gives them to you, that means that you will be able to evaluate the circuit exactly on the input x1, x2, up to xn, because you have the keys that correspond to those bits in the x. And then, it's too much, huh? Okay. Anyway, what does this have to do with one-time programs? It's sort of obvious, right? Because these keys, I could put them in my rocks. And then if my rocks have the property that you can only read one at a time, one either left or right, then you could only evaluate this circuit on one input. The particular input, you know, that is specified here on the right. Okay, I think that's enough for that. This is sort of how you garble gates. So adapting to our setting, as I said, essentially you do the garbled table thing. So you have these encrypted truth tables. That's the software. Then the hardware are the rocks, okay, where you put the keys, which are the keys on the inputs to the circuit. And this is all good and well. It actually fails, but we have to work a little harder, but we can, and I'm certainly not going to get into that. Wrapping up, I said the compiler cost a lot. Okay, so if you think about this method of garbled circuits, I took a program, a short program that ran for a long time. Then I produced this circuit, which is huge, as huge as the execution of the program. So instead, what we can do now, which is a later version, is that if you had something called homomorphic encryption, fully homomorphic encryption. So this is actually an amazing paper that just came out. And the idea of fully homomorphic encryption is that you can start with the encryption of M, okay, and then for any function, okay, any function f, you can produce the encryption of f of m. So instead, without decrypting, without figuring m, then computing f of m, and then encrypting again, you could somehow generate ciphertext of essentially an encryption of a function of m. Okay, and this was an open problem. People didn't believe possible, but now, just recently, there was a paper, and like last year, that enabled to do that. And it turns out that what this enables us to do in this setting is how to compile a function into a one-time program in a much more cheaper way than we had before. So now the program size, instead of before, which was the time to run your entire program, it's now just essentially K is a security parameter here, and M here is the size of the encryption. Never mind, this is too much detail. But in any case, the point is that we are completely independent of the size of the running time of the program. We are really dependent on things that have to do with the kind of cryptography that we're using. That's how that's how the software size blows up. And I think that becomes something that maybe is doable. The real question underlying this whole thing is, are these rocks reasonable? Is that a reasonable hardware assumption? Can you replace it by another hardware assumption that is considered a reasonable one? You know, that is already up to the hardware people. You know, it's up to your belief system. But it's certainly clean and easy to think about. Okay, how do you get that functionality? Okay, so in summary, I think what I wanted to convince you is that obfuscation, this whole thing about transforming programs into these scrambled programs, is a very powerful paradigm for solving cryptographic problems, you know, like for delegation and so forth, way beyond what it's used for in industry. These one-time programs is a new primitive. It seems to have some applications. I think there are more. And I think another interesting question from this research is really, what is a reasonable hardware assumption? You know, is it reasonable to think that there's a secure hardware that does cryptography? Is it reasonable to have secure memory? Because it seems that you can get a lot out of a secure hardware assumption, and even from a very simple one. And you know, it's a good question to see what other kind of secure hardware is out there and what we can get from it. That's it.